Good afternoon, everyone, and welcome to today's joint EOL-ACOM seminar. For those of you who may not know me, I'm Sarah Woods, and on behalf of EOL and ACOM, I'm pleased to introduce Dr. Nathaniel Brockway, postdoctoral researcher at the University of Alaska Fairbanks Geophysical Institute. Dr. Brockway earned his doctorate in atmospheric and oceanic sciences with an emphasis in chemistry and radiation from the University of California in Los Angeles. There, his master's work centered around developing a global correction function for the OMI-BRO dataset, and his doctoral thesis delved into airborne remote sensing of radical precursors in biomass burning smoke plumes, looking at emissions, chemistry, and radiative transfer. Dr. Brockway has airborne remote sensing experience deploying DOAS instrumentation on both the NASA DC-8 for FireX and the Purdue ALAR, recently for CHACHA. This recently took him up to Utqiagvik, Alaska, for which EOL provided field catalog support as well as drop zone support. To hear more about these Arctic measurements and HAIDI, please join me in welcoming Dr. Brockway for his seminar, Vertical Profiles of Bromine Monoxide via Airborne Remote Sensing.
Yeah. There we go. Thank you all for being here. So today I'm going to be talking about vertical profiles of reactive bromine measured in and around Utqiagvik last spring. And obviously, as the title says, measured via airborne remote sensing. So all of the data I'm going to be showing today was obtained during the CHACHA field campaign, which took place last spring, based out of Utqiagvik. And this campaign utilized 2 research aircraft as well as a ground-based research station, all based around studying halogen chemistry. So the 2 research aircraft we used can be seen in this photo here. In the foreground is the Purdue ALAR aircraft, which is the aircraft that my remote sensing instrument was on. So I'm going to be focusing on that aircraft today. In the background is a University of Wyoming King Air aircraft, which had much more in situ instrumentation on board. It had SIMS to look at gas phase halogens, pills to look at particle phase halogens, and then a lot of instrumentation to look at particles and cloud and water droplets. But again, I'm not going to be talking about those much, but hopefully in the near future we'll start to see some data from that aircraft. So I also want to start out by thanking everyone who was involved in this field campaign, especially everyone who got ALAR up and running throughout the entire campaign. Chiefly the mission scientist, Chris Hodgeny, who was in the aircraft for every flight and was responsible for manually collecting all of the data. So the reason that we care about reactive bromine, especially in the springtime Arctic, is that it leads to ozone depletion events. And I'm showing a very simplified chain of reactions here, but you can get the general idea. So basically, bromine molecules photolyze pretty rapidly in daylight, forming bromine atoms, which then destroy ozone. And then there are several kind of recycling pathways. So BRO reacts to form different reservoir species, but many of those reservoir species hydrolyze on surfaces, and the subsequent heterogeneous reactions can then expel bromine molecules. This is significant. Hopefully you can tell that in this scenario you have 1 bromine atom depositing onto a surface and 2 bromine atoms coming off. So this is the kind of so-called bromine explosion that leads to ozone depletion events. And here I'm showing a time series of an ozone depletion event that we observed during CHACHA. This was from the ground-based research station by Jose Fuentes' group. And you can see in this figure that there's a several-hour period where ozone concentrations were less than 5 ppb. So these are pretty drastic circumstances, and they can be pretty widespread. And they are particularly noteworthy because during these times of decreased ozone and decreased OH, the oxidative capacity of the atmosphere is really driven by radicals. So, it's really driven by halogens. So the halogens in the springtime Arctic are quite a large driver of the overall atmospheric chemistry of the area. And there are still many uncertainties associated with this chemistry, particularly in the multi-phase chemistry that produces these bromine molecules. So kind of due to these remaining uncertainties, it's important to kind of continuously improve our understanding of this chemistry. So I want to take a second and point out bromine monoxide here in this reaction. So this is the molecule that I'm going to be talking about and that we observe with our instrument. So it's formed due to that ozone destruction. So anywhere we see this bromine monoxide, it tells us that's an area where this chemistry is occurring. It's a tracer for this ozone depletion. Right? So this chemistry is also happening in a rapidly changing environment. I think we all know that the Arctic is warming considerably faster than elsewhere in the mid and lower latitudes. And this will and is having impacts on this chemistry for several reasons. The first reason is that one of the commonly thought sources of bromine, reactive bromine in this region, is due to snowpack on top of saline sea ice that releases these bromine molecules due to those reactions I showed in the previous slide. And it's been seen that first-year sea ice has higher concentrations of bromide than multi-year sea ice, indicating that it could impact the source strength of these bromine emissions. So as the distribution of this first-year sea ice changes with warming, that could potentially impact the source of reactive bromine in the area. On top of that, as soon as the snowmelt kind of starts in late spring, this chemistry shuts off because the surface area that those multi-phase reactions are occurring on decreases so much. So obviously the timing of that snowmelt is impacted by warming. And lastly, any dynamic changes that occur in the area due to warming will obviously impact chemistry as well. So we're going to be focusing in on the northern area of Alaska right here. I just want to point it out before I zoom in on the next slide. So the CHACHA field campaign took place from roughly mid-February to mid-April of 2022. It was based out of Utqiagvik, Alaska, to study halogen chemistry, kind of centered around these three main tenets. And I should actually point out real quick that the map here is a MODIS composite image, which differentiates sea ice/snow from clouds. So all of the blue is sea ice or snowpack, and you can see a little bit of clouds over the open water. So obviously, being on the northern edge of Alaska, there's a lot of sea ice surrounding Utqiagvik, so there are a lot of sources of reactive bromine in the area. And on top of that, as the kind of year progresses, as you get later into the spring, you get these openings in the sea ice called leads. That's shown on the left side of this figure where you can see the open water. And that open water is considerably warmer than the surrounding sea ice, so you get enhanced convection and cloud formation over those leads. And those dynamic changes in that processing by water droplets impacts this halogen chemistry. And then lastly, a little over 300 kilometers to the east is Prudhoe Bay and the Prudhoe Bay oil fields. It's obviously a larger area than just this star, but there are a lot of anthropogenic emissions in the area associated with this oil extraction. And again, those anthropogenic emissions will impact this chemistry. So the kind of specific questions that I'm going to be answering today is what is the current state of halogen chemistry in the Arctic? Again, it's a particularly important driver of the overall atmospheric chemistry of the area, and in this rapidly changing environment with these many uncertainties, I want to just look at what the state of it is at the moment. And I also want to talk about the vertical distribution of that chemistry. So there are really very few observations of halogens with vertical resolution in this area. There have been many ground-based studies to look at this chemistry, and there have been several max DOAS studies that can give us some information on the vertical structure of the trace gases, but they can really usually only resolve about two vertical parameters. So we don't have a very fine resolution understanding of this chemistry, meaning that we don't have many opportunities to validate modeling of the areas. Then on top of that, any differences, I want to kind of investigate any differences that we see between different profiles, different profiles and some of the causes behind those differences. And then lastly, again, as I measured, I'm using a remote sensing instrument. So I also want to talk about what is the best way that we can measure this, that we can observe this chemistry with a remote sensing instrument. Again, the King Air was mostly used for the in situ observation, so their flight path was quite a bit different than the Purdue ALR aircraft. All right. So to start out with that last question, we used the Heidelberg Airborne Imaging DOAS instrument on board the Purdue ALAR aircraft. So this instrument actually contains two spectrometers. One is a Nader whisk broom spectrometer that basically just scans back and forth. It scans pixels over the surface. And then it also has a forward spectrometer that reads light onto a CCD, and that light comes from a total field of view of 7 degrees. And we can bin different channels of that CCD to get different discrete viewing angles. So in this setup, we actually have 4 different viewing angles for this forward spectrometer, all centered around a limb geometry or kind of tangent to the Earth's surface. So this is the spectrometer I'm going to be focusing on today. So they're all kind of, horizontal observations with slightly different viewing angles, but those slightly different viewing angles actually have slightly different sensitivity to different altitudes of the atmosphere, and we can use that slightly different information to determine something about the vertical structure of trace gases, at least located around that flight altitude. And I'll be coming back to that point a few times. All right, so HAIDI is technically an airborne max DOAS instrument, so airborne multi-axis DOAS instrument. And the DOAS method works by basically, it just measures scattered sunlight into the telescope, and it fits that spectrum with a reference spectrum to account for solar structures, and then with absorption cross-sections of different trace gases. So in this example here, I'm showing 2 trace gases that were fitted, BRO on top and NO2 on bottom. The black line is the absorption cross-section, and the red line is the absorption cross-section with the fit residual. So you can see how we actually identify these trace gases in the spectra. The coefficient of this fit basically tells us something about the quantity of the trace gases in the atmosphere. And in this case, those coefficients are negative because there's an amount of radiation missing from our observed spectrum. So that's telling us that there's a absorption in that spectrum, that measurement spectrum. All right. So again, I said that we use a reference spectrum for our fits, and I'm using this slide to kind of explain how that works. So for this project, we used a high altitude observation as our reference spectrum, and this accounts again for the solar geometry or the solar structure of the spectrum, as well as the kind of instrument function of the spectrum. And in this case, that high altitude means 1,000 meters or something like that, but it's generally, there's less BRO and NO2 absorption in that spectrum than there is closer to the surface. So this works because when we're considering 2 observations, one at the surface and one at 1 kilometer altitude, basically light travels through this is a very simplified view, but basically we can think of the average path that a photon takes to get to our instrument. So light travels through the upper atmosphere. There's some scattering event at the flight altitude that then scatters that photon into our spectrometer. Because we're talking about observations at the surface in 1 kilometer, what's happening above the aircraft is relatively constant for both of these observations. So when we use this reference spectrum for our fit, we're basically canceling out whatever's happening above the aircraft. So this basically takes away any stratospheric BRO absorption in the spectrum, and we're really left with what's happening below that reference spectrum. So in a case like this, where I'm trying to show that the trace gas is located closer to the surface, you're going to have much higher absorption in the measurement spectrum from the surface, and that's really going to dominate the measurement. So we technically measure a differential slant column density, where a slant column density is the number of molecules along the light path that actually reach our telescope, and the differential slant column density accounts for the fact that that reference spectrum has some absorption in it, so it's offset by that value. All right, so as a result, the differential slant column densities that we retrieve are affected by the location and the amount of the trace gases, where that is in location to the aircraft, as well as the solar and measurement geometries. And we're also, our observations are also impacted by how light actually reaches our telescope, and that's going to be largely affected by particle extinction as well. All right. So here's a little cartoon to kind of explain some of these some of these ideas. So in this case, there's a plume, lofted above the surface. In this first case, where we're below the plume looking up, we would have very good sensitivity to this plume. We would see a clear signal from it. In this second case, hopefully you can see that the lower path length would spend light going into the lowest viewing angle would spend more time going through that plume than our upward viewing angles. So that would have a larger differential slant column density. We would actually see a pretty significant difference between those 4 different viewing angles. And then in that third case where we're above the plume looking up, we now no longer have any sensitivity to that plume. But again, this is all going to be impacted by solar geometry and particle extinction and what kind of particles, forward scattering versus back scattering particles, things like that. So in order to account for that, we use observations of O4 to understand a little bit about how light gets to our spectrometer. And O4 is an oxygen dimer, so it's just formed by collision of O2 molecules. And since we know the profile of O2 based on temperature and pressure, therefore know the profile of O4, we can basically say, this is where O4 is. This is how much O4 we saw in our different viewing angles. So there needs to be this much, this particle extinction at this altitude to explain our observations. All right. And I want to pause a second and actually kind of show some real examples of this. So obviously these are pictures, so we're considering how visible light is affected by, these, but the same holds true for the UV. So in this first case on the top left, this was a relatively hazy day. Hopefully you can see a little bit of detail in the surface, but as you look towards the horizon, it's very hard to make out a horizon. So again, this is an instance where our observations would be impacted by this particle loading, and that's something that we need to account for. On the top right is a picture actually from the same day, but you can see that as you look towards the sun, the particles obviously look a little bit different, right? They look a little bit closer, giving us some information on the type of particles they are, and also indicating how solar geometry plays into our observations. In the bottom left case is an instance of a clear day, so you can clearly see a lot more detail on the surface. The horizon is a lot easier to make out. And then the last case on the bottom right, hopefully you can make out that there's kind of this thin brown line hanging just right above the horizon. So this is actually a plume from Prudhoe Bay, so likely includes quite a bit of NO2 and particles. So again, where the aircraft is in relation to that plume will dictate how we actually observe it. All right. So hopefully I've made clear to you that there are many different parameters that impact our observations that need to be accounted for. And we account for those using radiative transfer modeling. So this basically is used to describe how light reaches our telescope. On the left are some of the different parameters that need to be accounted for in the radiative transfer modeling and the source of the data I used. And on the right is an example output from the radiative transfer model. So this is showing a box air mass factor, where a box air mass factor basically explains the horizontal path length enhancement of light through each grid of the model. So to put this kind of in a little more tangible terms, this orange line here for this observation closest to 0 degrees, closest to the limb, this has our highest box air mass factor, which makes sense because it's closest to the horizon. In this case, it peaks at about 70. So that tells us for this grid of the model, this 50-meter grid, vertical grid, that light traveled 3.5 kilometers horizontally to get to our telescope through this layer of the atmosphere. So it tells us which levels of the atmosphere we're most sensitive to, because if light travels through one layer of the atmosphere more than the others, then the trace gas absorption in that layer of the atmosphere is going to dominate our signal, right? So and again, as I said earlier, and hopefully you can tell here, each of these observations is most sensitive to, or right around that flight altitude. But again, there is slightly different sensitivity for these different altitudes. So we can use that different sensitivity along with our observations to then do an optimal estimation and inversion to determine the mixing ratio of the trace gas. All right. However, as you might also be able to see here, this only works around that flight altitude, right? None of these viewing angles has a particular sensitivity to the surface, at least for this observation. So in order to get more information, we use multiple observations at different altitudes. And we did it with a kind of specific flight maneuver that we called porpoising, where we basically consistently changed altitude between a top altitude of around 1,000 meters and a bottom altitude of around 100 meters. And we would, change from top to down to bottom and back up without changing heading. And that's particularly important as it greatly simplifies the radiative transfer of the situation. If we were doing a corkscrew, for instance, the solar geometry is continuously changing for each of our observations, and it's not even constant for a single observation. And then on top of that, the roll of the aircraft would then change the 4 viewing angles that we actually have. It's just a lot more to actually account for. So by doing this down and up porpoising without changing the heading, it makes it quite a bit easier. So for each one of these down and up portions of the flight, we package all of those observations with all of the modeling to retrieve a single BRO and a single NO2 profile. So we clearly give up some horizontal resolution in this case. So these porpoises usually average about 30 kilometers. But for a molecule like BRO that doesn't really have a sharp source or something like that, this is a pretty fair trade-off for the increased vertical resolution that we get. All right. So as I briefly mentioned, and I won't talk about the method that much, but the first step is to retrieve the particle extinction profile. So again, we use all of these observations and we say, we know this is where O4 is, this is how much O4 we had at each of these altitudes, so there must be this particle extinction at each of these altitudes. After we do that, that particle extinction is then fed back into the model for the box air mass factor calculations for BRO. All right. So an example BRO retrieval is shown here. So on the right side of this figure in blue is the actual profile that we retrieve. In black is the a priori profile. So that's basically our first guess without any prior information that we put into the model. And then on the left is the averaging kernel matrix. So this tells us, this is colored by altitude. So each of these lines is for a different altitude. And they tell us how much information for this altitude comes from observations at all altitudes. So in an ideal world, this averaging kernel matrix would be 1 at each of these lines would be 1 at their own altitude and 0 at all other altitudes. And you see that we actually get fairly close. So, for instance, if we look at this, the surface averaging kernel, you can see that, say roughly 80% of the retrieval at that altitude came from observations in that model grid. So that tells us that each of these retrieved mixing ratios is relatively independent from the other. And you can also see in this that we can't really reduce the size of our model grid anymore, because that would just put more of the onus on other model grids for the retrieval. So we wouldn't actually gain any more information. And we know that because the trace of this averaging kernel matrix is the total degrees of freedom of this retrieval. So that tells us how many independent pieces of information we can actually retrieve from this. So in this case, you see we get close to 17 degrees of freedom, which tells us, for a 50 meter model grids, we basically can retrieve the profile below 850 meters or so. So throughout the campaign, really, we have averaging kernels that look like this between the altitudes actually flown for each porpoise. All right, and I will show that in this slide here, which is a histogram of all of the degrees of freedom from each of the porpoises throughout the campaign. So on average, we retrieve 17.5 degrees of freedom. But again, this is really just telling us what altitudes were actually flown for each one of these porpoises. So in a case where you see 40 degrees of freedom, that just means that our porpoise went from the surface to 2 kilometers altitude and back. On this plot, I'm also showing 2 pieces of literature that do the same method that reported 10 and 12 degrees of freedom, respectively. The BIDAR 2013 paper is actually with the CU Boulder AMAX DOAS instrument. And you can see that they're, a little bit less than many of the degrees of freedom retrieved here. And that's largely due to that model grid spacing. So in both of these papers, in the Prados-Roman paper, they did a profile from basically the surface to 10 kilometers altitude, but with a little over a kilometer grid spacing, therefore retrieving 10 degrees of freedom. Similarly, the BIDAR paper went from, I think, about 3.5 kilometers altitude to around 600 meters altitude on a low approach, but with 250 meter grid spacing, get 12 degrees of freedom. So, basically, this method could certainly retrieve more information with finer grid spacing, though that comes at the cost of computational time. And I think that that's also a much different discussion in 2013 than it is today. So with modern computing speeds, this is an area where we could actually retrieve a little bit more information from these profiles. All right. I will say that we also have another clear advantage in this field campaign in that we don't need to worry about running into anything. This is a set of figures from a porpoise, and you can see that there's no populated areas, there's no tall buildings, there's no vegetation that we need to worry about. So in this case, we could fly as low as a pilot was comfortable flying. So I will see that was, that helps for our degrees of freedom. All right, so that basically sums up the methods portion of the talk, and now I want to start talking about some of the chemistry results, and I'll start just by showing the average BRO profile retrieved throughout the field campaign. So this is shown as a box and whisker plot, where the edge of the boxes is the 25th and 75th percentiles. And as you can see, we regularly retrieve the highest concentrations at the surface, or highest mixing ratios at the surface, and they quickly decreased aloft. However, you should also probably be able to tell that there's a lot of variability around this mean, really at all levels, but especially below, say, about 400 meters altitude. And this variability certainly deserves to kind of be investigated more closely. And we looked into this using a clustering algorithm. So the clustering algorithm basically just looks for common profiles that regularly occurred throughout the field campaign and average the profiles that fit into each of these buckets. So I'm showing we basically found four different clusters throughout the 245 porpoises from the field campaign. And I'm showing those here in order of kind of descending number of observations. Also on these plots is the LTVCD and the F200. So the LTVCD stands for lower tropospheric vertical column density, and it's just the sum of all molecules between 0 and 2 kilometers altitude. So this gives us some idea of how much total bromine monoxide there is in this observation. And the F200 tells us the fraction of that below 200 meters. So that basically tells us how surface-based this profile is. All right. So the most common profile that we saw was a low BRO, and it's really more of a low column BRO observation because there's still 20 ppt at the surface, so nothing to shake our heads at. But it quickly decreases aloft, and it corresponded with our lowest vertical columns. The next most common was a high surface BRO, which similarly to the low BRO case, there's very little BRO aloft, but you have about twice as much BRO at the surface as before. The next profile is the high total BRO high total BRO cluster. So similarly, quite a bit of BRO at the surface, but we actually started to see more of that BRO getting lofted higher into the atmosphere. And then the least frequently observed case is the lofted BRO case, where the highest mixing ratios were actually seen several 100 meters above the surface. And that actually corresponded with our highest retrieved columns. So I will come back to these lofted BRO profiles in a few slides, but I should also point out real quick that our results have a pretty obvious clear sky bias, and this is for a few reasons. The first is that we can't fly in inclement weather, so there's been a lot of work on BRO associated with blowing snow events or blizzards and things like that, and these observations really are not indicative of those events. We just simply can't observe those events with a manned aircraft for obvious reasons. So this, isn't really, related to those necessarily. The second reason is that the aircraft that we were on actually didn't have de-icing on the wings, and the pressure probe on the nose of the aircraft also has some open electrical contacts. So we could not fly through clouds or haze for fear of icing on the wings or of water impacting that instrument. And then lastly, the DOAS method actually has kind of a questionable time retrieving trace gases co-located with clouds or haze due to that increased multiple scattering. It becomes quite a bit harder to determine where light actually came from before it got to our telescope. All right, so So based on these profiles, I now want to talk about some of the kind of reasons behind the profiles and the differences between them. First, looking at meteorology. So for these three plots on the left is the potential temperature profile, though it's offset by the value at 500 meters. So I really want to look at the stability of the lower atmosphere as opposed to the absolute temperature of the system. And then in the middle is the wind speed, and on the right is the particle concentration from the smallest bin of the particle sizer on board ALAR. I'm only showing one bin for reasons that I can explain later if you're interested, but just trying to show it as kind of a proxy for the particle loading in these systems. So, and then lastly, I'm also cutting these profiles off at 100 meters, and that's because the kind of lowest altitude that we flew to was variable. So this allowed us to some consistency because most of them went below 100 meters. Unfortunately, we can't see what's happening at the surface as a result, or closer to the surface, but the trade-off was getting more observations. So looking at these plots, I think we can clearly see just how stable these low BRO and high surface BRO cases are, with a very, very sharp negative lapse rate. Which makes sense, right? In these cases, we're basically having BRO formed on the surface due to the multi-phase chemistry I talked about at the beginning, and then in these incredibly stable atmospheres, it's stuck at the surface, and that's why we have high concentrations at the surface, very little aloft. Now, I should also say that in the springtime Arctic, the kind of background environment is an incredibly stable atmosphere. So although the high total BRO and the lofted BRO cases never actually get to neutral, they are clearly less stable, at least over the lowest few hundred meters, than the other cases. And again, that explains how some of that BRO is lofted higher into the atmosphere. So the kind of meteorological conditions actually explain quite a bit of the variability between these retrieved clusters. And then looking at the wind speed and particles, we can also clearly see just how much of an outlier these lofted BRO cases are. But before I talk about those lofted BRO cases in more detail, I want to show one nice feature of these clusters, and that's that it makes it very easy to see spatial changes in the BRO profiles. And I'm showing that there's many cases where there was a pretty clear gradient between the retrieved clusters, and I'm showing probably the best one here. So the red line is the flight track for this day. The cluster markers indicate the kind of center of our down and up porpoises, and the marker itself tells us which cluster the retrieved BRO profile fit into. So for this day, you can see that as we flew out over the tundra, we exclusively saw high surface BRO cases. However, as we flew back, over the sea ice, I think I said tundra. As we flew out over the sea ice, we exclusively saw high surface BRO cases. Then as we flew back over the tundra, we saw many more high total BRO cases. And again, as we saw previously, that can largely be explained by meteorology. I know it's a very slight difference, but there is a slightly higher boundary layer over the tundra, or was a slightly higher boundary layer over the tundra, which explains how some of that BRO is lofted higher into the atmosphere. Right? Now, this holds true except for this area just downwind of Prudhoe Bay. Prudhoe Bay is indicated with this star here, and in this area just downwind, we retrieved exclusively low BRO cases. And this is likely due to some kind of direct gas phase interaction between BRO and NOx. And the reason I say that is, one, that there is some literature to support that claim, but also throughout the campaign, we saw 11 profiles that were clearly impacted by above background levels of NOx, and 10 of those profiles fit into low BRO categories. So to kind of look a little bit more closely into this interaction, I want to zoom in on this area. So hopefully you can tell from the flight track that we did one transect downwind of Prudhoe Bay flying to the north. We turned around and did another transect flying south, and then we turned towards the west and flew back towards Utqiagvik, and we intersected that plume well downwind. So again, I'm going to zoom in on that area, and for that same inversion I do to get the profiles I've shown so far, I am now going to do on just 10 observations at a time. So we now have quite a bit more higher horizontal resolution, but we're going to lose some information in the vertical. So in this case, here I'm showing the retrieved mixing ratios of NO2 and BRO from this time. For these observations, we have about 4 degrees of freedom. So that tells us we can retrieve the mixing ratios in about a 200-meter swath around the aircraft, which is centered around 125 meters or so throughout this time. All right. So hopefully in this you can make out the times when we transected the plume. So this is that first transect as we flew to the north. This is the transect as we turned around and flew back south. And then this is that plume that we intercepted as we flew well downwind. This was about an hour and a half downwind of Prudhoe Bay based on wind speeds. And there are basically two takeaways I want you to have here. So the first is that in each of these areas, we see BRO depleted in the gas phase. The kind of spatial correlation isn't perfect. Part of that's because since I'm using fewer observations, there are some higher uncertainties in this retrieval. But in each of these areas where we see higher NOx, you also see lower BRO. So there clearly is some gas phase interaction between BRO and NO2 occurring here. The second takeaway I want you to have, and especially on this kind of in this middle area, is that even inside this plume, there is still a considerable amount of BRO at the surface. And that could be to two reasons. It could be that this is a case where the NOx plume is lofted above the surface, so the BRO at the surface is just not impacted by the NOx as much. Another reason could be that even in this NOx plume, there's still BRO or reactive bromine recycling occurring on the surface that is sustaining those BRO concentrations. So these are observations that we previously have not had. So it will be very interesting to do some chemical modeling with these observations to get a better understanding of how anthropogenic emissions actually impact this halogen chemistry. So now I will go back to that lofted case that I teased a little bit earlier. The lofted BRO cluster was the least often observed cluster throughout the field campaign, with 15 total clusters observed throughout the field campaign, and 11 of those occurred on this single day. So I really kind of want to focus in on this day and see a little bit about what's different. So first off, looking at the map, we can see how widespread this event is. It's really observed basically throughout our entire measurement region. So as I showed previously, these lofted BRO clusters were associated with lower wind speeds and higher particle loadings, and our particle extinction retrieval supports that. So on the left of this plot here is that particle extinction retrieval using the O4 observations that I mentioned earlier, and on the right is the mean BRO profile retrieved on this day. So this day had our second highest AOD of the field campaign, and on top of that, we also see that the particle extinction peaks several hundred meters above the surface at the same altitude that the BRO mixing ratio peaks. So many studies have seen a correlation between BRO amounts and particle extinction, indicating that reactive bromine is emitted from the surfaces of these lofted particles due to multi-phase chemistry. So it was very nice that we had a case that kind of confirmed these pieces of literature that we can also study a little bit closer. One thing that we're interested about is, what is the source of these particles? Are these particles that were advected from elsewhere, or are these particles that were lofted from the surface due to increased turbulence on this day? So that will be something that we'll look at in a little bit more detail going forward. All right. So to summarize some of these findings, the first thing is that we now have many more vertical profiles of BRO that we can use to validate chemical modeling. We also have it in some pretty specific circumstances. So we have it inside of anthropogenic emission plumes, and we also have some lofted BRO profiles. So we have many observations that we can use really to understand this halogen chemistry quite a bit better. Secondly, a majority of our observations fit into a cluster that had its highest concentration at the surface, which really just indicates how important the snowpack is, regardless of if it's over sea ice or tundra, but how important snowpack is as a recycling mechanism for this reactive bromine. And it also was very nice to see that the meteorology accounts for quite a lot of the differences that we see between these different profiles. From a method standpoint, this porpoising maneuver works very well to retrieve high-resolution profiles of the background atmosphere. It would not be appropriate to try to study a plume with this measurement technique, most likely, because that spatial range is too large to see some of these sharp changes. But for kind of understanding the background trace gas profiles, it was very effective. And this method could certainly be expanded to kind of different uses. So Mostly uses of AMAX DOAS instruments require some type of external housing. I'm showing a couple examples of that here. So on the left figure is the bottom side of the Purdue ALR aircraft, where you can see this metal fairing that was built around our telescope. But without that fairing, it's basically just a hole in the floor of a aircraft, which you obviously cannot do with most aircraft. And then on the right side of this page is the telescope housing for the UCLA Mini DOAS on the NASA DC-8. And again, you can see that they took out a window panel and put this in to be able to pressurize it. So these are obviously pretty intricate setups that do give us quite a few benefits. But there is certainly an opportunity to build kind of a less intricate setup for use on for easier use. So for instance, I just kind of put together two example AMAX DOAS setups here. So this top one is kind of an example of something that maybe you could build to put in the passenger seat of a light commercial aircraft, stick a telescope out the window, and hire a pilot to take off and land for 2 hours or something like that. Just kind of a much easier setup than drilling a hole in the floor of the aircraft. And then on the bottom is an example that maybe could be put on a drone or a UAV, which are obviously becoming quite a bit more popular in our field. So there are definitely some different options to create kind of simpler instruments that utilize this technology. So obviously all instruments have trade-offs, but some of the nice things about these instruments is you don't have to worry about inlet losses. There aren't calibrations that you need to do in the field, really just take a few reference spectra of mercury. And I'm also listing some of the trace gases that you can absorb or that you can observe with this technique. So I think the phones in all of our pockets are pretty good evidence of the recent advances in optical technology over the past 10 years, and these instruments are really just kind of relying on these advances to create kind of some nicer instruments to observe some of these trace gases, right? So from here, there are a few things I want to do. One is to compare these observations to satellites. Satellites notoriously have a tricky time measuring BRO for a number of reasons. So it's important to see how our observations compare. And along with that, our observations actually have some pretty important implications for satellites. What I mean by that is if we compare this low BRO case to this high surface BRO case, again, there's a factor of 2 difference in the mixing ratio at the surface. But if we look at the LTVCD, the vertical column density, there's very little change between these 2 cases. Adding in the fact that satellites are also least sensitive to the surface, a satellite likely would not be able to differentiate these 2 cases, even though the atmospheric chemistry at the surface could be vastly different in these 2 scenarios. So that's something to consider with satellite observations going forward. Obviously, we would love to do chemical modeling of many of the various scenarios we observed throughout the field campaign. And lastly, I'm also interested in doing NO2 flux measurements, mostly with the Nader instrument. Again, there was a lot of NO2 emissions in the area, so we would like to compare our flux measurements with in situ observations and with satellite instruments. So thank you for listening. This picture on the right is my shameless plug to try to get you to do Arctic research if you haven't already. And I would love to hear any questions that you have.
Thanks, Nathaniel, for that super interesting talk. Reminder for those online, you're welcome to enter your questions in Slido. There will be a box beneath the video screen. Do we have any questions from the room?
The lofted BRO case, I noticed it was southwesterly winds. Having been in Barrow for a while, Utqiagvik for a while. Back then it was still Barrow. Do you remember whether you saw any ozone depletion on that day in Barrow at the ground?
That's a good question. I don't remember off the top of my head. I don't believe this was one of kind of the main ozone depletion events that we've focused on, but that doesn't mean that there wasn't ozone depletion on that day. I actually am not sure. I need to double check. Yeah. But I'd be happy to look and get back to you.
Thanks. I think we had one more in the back.
Thanks. That was a great talk. Trying to think of which question to ask. Did you ever not see BRO?
Not often. There were a couple, there was actually one day that was particularly warm, and that day we saw very little BRO. I mean, it was basically just detection limit throughout the flight. But that was kind of the exception in the campaign.
It's, it's obvious maybe, but ozone and BRO at some level should be anti-correlated. And if you have, no, correlated. So if you have no ozone, you can't have BRO. So I'm just kind of surprised that none of your plots are retrieved normal, reoccurring profiles show complete ozone depletion, hence no BRO. I guess that just wasn't a thing.
Yeah, that's fair. I think that we probably do have a few profiles of that just fit into that low BRO cluster that average out to 5 ppb or at 75 meters altitude. But I'm sure that there are many. Well, I know that there are many profiles that we saw that were basically zero.
Okay, one more quick one. Do you have any plans of doing 1D modeling? Because I'm not sure a box or anything is going to tell you a ton here.
Yeah, I personally would not like to have any plans of 1D modeling. We'll see if I have a choice soon. But yes, I think that we would love to do some 1D modeling with this data.
That makes a lot of sense. We have a question online from Adriana Bailey. Thanks for your presentation. I may have missed this, but where do your prior profiles come from?
Oh yeah, it's to some extent a guess. There are some pieces of literature that I rely on to kind of build that out, but it's also just a little bit of a song and dance to try to get something that works without putting too much kind of bias into the retrieval. If I assume that there's 20 ppt at the surface, then I end up with profiles that have 10 more ppt than before, in different shapes. So part of it was, so a lot of it comes from previous, studies, and then some of it just comes from trying to kind of maybe be a little bit more conservative with the amount that I expect there to be.
Just quick question about the retrieval, the DOAS fit. Did you see any cross correlation with formaldehyde?
Not much. So in this case, I actually didn't fit formaldehyde because the fit was just a little bit better because of that correlation. But I did several fits with formaldehyde, and in these plumes, I even went out looking for formaldehyde, and we never really saw it above detection limits. So for that reason, I didn't include it in the final product.
So I'm curious, have you done any comparison between your remote sensing measurements and, say, in situ from the King Air?
Not yet. I actually haven't looked at the King Air data yet, but I'm really looking forward to it, honestly. Yeah, I'm very curious how they match up.
Cool. Sounds like there's a lot of exciting work yet to come.
There sure is, yeah.
Speaking of future projects, so you mentioned that you had to cut off, the very bottom of the profiles. Have you thought about using ground-based measurements or flux towers or perhaps something other than an aircraft to get at that real bottom boundary layer?
Yeah, that'd be great. We do have some flux tower measurements from Utqiagvik during the field campaign that we can use. And I definitely plan on doing that. One of the tough things about the Airborne campaign, though, is that, some of our observations are 400 kilometers away, so I'm not sure how indicative that flux tower is to what's happening for that observation. But that's definitely still, good data to compare to. Yeah.
Sure. Any other questions in the room?
Maybe a naive question from someone who doesn't really look at chemistry a whole lot, but as you're doing these porpoises, is there a noticeable difference in BRO content going down versus up based on the aircraft perhaps modifying the BRO profiles as you're ascending or descending?
Yeah. So it is interesting, actually, just looking at the raw data. When you're descending, you kind of see all of them go up, and usually whatever one is closest to 0 degrees gets the highest. And then the second we turn around, those kind of flip. So now the lowest one shows the highest. There's not that kind of impact is well accounted for with the radiative transfer modeling. So, if I do retrieval with just the down and just the up, they come out very similar. Yeah.
So I have one more question. You mentioned AMAX and mini DOAS. What's the difference between them?
The mini DOAS is an AMAX DOAS. It's just the name of theirs. Yeah.
Oh, okay. Just curious. Do we have any more
Fair
questions?
question.
All right, then let's thank Dr. Brockway one more time.